Okay. Okay, so I'm going to start now. Don't need any introduction. It's day 3. Everybody's got their spot. I see that everybody's in the same spot that they're going to be in for the next month. You know, you could confuse people by moving around, but I'll bet you don't. So today I'm going to talk about some theoretical reasons that we think there are problems in the Higgs sector. So this is going to be less phenomenological than the first 2 days and a little bit more theoretical about problems with the standard model and what we can learn about the Higgs just by thinking about it. And then tomorrow I think I'll talk about SMEFT and how to go forward in the future. Only one person gave me mistakes in my lectures, and it was a blooper that they found. So I hope that more of you will find mistakes because I'm sure they're there. It's impossible to get everything right. Okay, so today I'm going to talk about exploring Higgs properties indirectly. So I'll talk about the oblique parameters, so-called ST and U. I'll give an example of how the Higgs contributes to the W mass and how precision measurements of the W mass actually contribute to our knowledge of the Higgs sector. And then I'll talk about the renormalization group evolution of the parameters and what we can learn about the Higgs sector by looking at the RGE. And I'll do a simple calculation of the renormalization group evolution. And then if I have time, I'll talk about extending the scalar sector. I have a lot of slides about the singlet model and the 2HDM, which I'll leave in the lecture notes even if I don't get to it. So my point is going to be today is that there are a lot of ways of learning about the Higgs boson. Okay. So quantum corrections, the easiest thing we know to calculate is the renormalization of the masses. Now that I have the middle screen down, I'll just point always at the middle. Calculating the 2-point function, it's not so hard. So I've got a W here, a W here, a Z here, a Z here, or whatever. And in general, the 2-point function is G mu nu times something plus K mu K nu times something. And what I'm going to do today, we only need the coefficient of the G mu nu piece. So it's pretty easy. So for example, the W mass, we start with our thing in the Lagrangian, which, as you all remember from day 1, it's G squared V squared over 4 is MW squared. Those are the unrenormalized parameters. Here's the renormalized W mass, and here's the 2-point function. And it turns out we can learn a whole lot about Higgs physics just from this simple example. And the largest numerical corrections to precision observables are typically from these 2-point functions. And I put this in italics here because it's not true always. If somebody says that's not true, I can give you an example where the largest corrections aren't from the 2-point function. But as far as the Higgs is concerned, it's usually true that everything is contained in these 2-point functions. Okay, so let's start by the simplest thing I can calculate. I'm going to calculate the Higgs contribution to the rho parameter. Now the rho parameter, as you remember, is mw squared over mz squared. Oh, there's a typo here. Theta w squared. I'll fix that. So the rho parameter is predicted to be 1 in the standard model. So we can measure experimentally the deviations from 1. And I didn't put any plots here, but I'll tell you the rho parameter is very, 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 very close to 1. Okay, so we're not allowed to have big contributions to it. So suppose I calculate the 2-point function of the Z, the Higgs contributions. There are 2 of them here. Okay, so those are the contributions of the Higgs boson to the 2-point function of the Z. And there are a lot more diagrams. I put this here. You can draw them down. There are diagrams with W's. There are diagrams with Goldstone bosons, depending on your gauge. So there are a lot more diagrams. These are the only 2 that contain the Higgs boson. If I just calculate these 2, I will find divergences. There'll be 1 over epsilon poles, which are canceled by calculating the whole spectrum of diagrams. But nonetheless, I can pull out the dependence on MH from these 2 diagrams because they're the only thing where MH comes in. Furthermore, these contributions alone aren't gauge invariant. So this is just pulling out a piece of the whole. So I'm going to keep only the terms which depend on MH when I calculate these guys. And what do I get? I get the rho parameter alpha over 16 pi cosine squared theta w, and it's a logarithm of mh squared over mw squared. So the rho parameter depends logarithmically on the Higgs mass. And now you should be a little surprised looking at these diagrams that you get a logarithm. Okay? And why should you be surprised? It's because let's pull out this diagram. Okay? So we got these diagrams. Here's a W, here's a Z. these diagrams here. So if I calculate this diagram, let's look at this guy. I calculate the 2-point function. There's a coefficient here, which is g squared over 2 cos squared theta w. There's a half, because it's a scalar in a loop. There's a 1 over k squared minus mh squared. So in dim reg, I just looked this up in my favorite book, and I get the answer. And it's mh squared, OK? So this guy is divergent, OK? So where do these mh squareds go? So I put together the two pieces, the w and the z. So here's the row parameters, pi ww minus pi zz. So it's got the front matter from these guys. And then there's a 1 over mw squared, same front matter, 1 over mz squared cos squared theta w squared. So the terms that go like mh squared cancel. And they cancel because of this relationship that mw squared is mz squared cos squared theta w in the standard model. So this is actually a consequence of the way the model is structured. So we don't get these terms which are mh squared. We only get the logarithmic terms that remain. So that tells me that these precision observables are not that sensitive to the Higgs mass because it's log mh. So let's beat this to death a teeny bit more, because this is the so-called custodial symmetry. Let's go back and look at the gauge boson mass matrix, and let's look at it in the basis of SU2 cross U1 bosons. So W1, W2, W3, those are the gauge bosons of SU2. B is the gauge boson of U1. So here's the mass matrix, V squared over 4, and then all the terms here. So these upper two, which are W1 and W2, you recognize those. Those turn into the W mass, g squared v squared over 4 mw squared. But now if you look at this a little bit more, if you turn off g prime, so you set the hypercharge to 0, this matrix has a symmetry. It's a rotation symmetry under W1, W2, and W3 are exchanged. And this is the custodial symmetry we're talking about. So this rotation symmetry here is broken by the hypercharge in Yukawa's. And it's kind of an accidental symmetry of the theory. But nonetheless, it's got these consequences. In particular, the Higgs precision observables are all logarithmic. OK. So let's keep going. Yeah?
Sorry, I don't see how that mass matrix leads to the logarithmic dependency.
I'm just saying that there's a symmetry. And this is the same symmetry that I have here. It leads to mw squared equals mz squared cos squared theta w. So if you turn off g prime, the z mass is equal to the w mass, because W1 and W2 and W3 are all the same. So in that limit, we have mw squared exactly equals mz squared cos squared theta w. So that's the symmetry that gives us the cancellation of the mh squared terms. OK, so what else can we learn from looking at radiative corrections? What about the W mass? So the W mass is predicted in the standard model. This is the value from particle data group. And it's a good resource for everybody if you're wondering what the latest mass is, to just look it up there. Yes?
So in the previous discussion, just going over, the Yukawas are kind of very clear spurions to...
Well, they break the symmetry.
Right.
Yeah.
But can we also, since G prime is a charge, is that also kind of, does it work the same way, where you can treat it as like the amount of G prime you have is the amount of symmetry breaking you have?
No.
No. Okay.
No. So in the Electroweak sector, I can calculate the W mass in terms of my inputs. And we always take the Z mass, G Fermi, and alpha as the inputs. And the reason why we do this is because they're extremely precisely measured. MZ 91 point blah, 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 alpha 1 over 137 point blah, 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 and G Fermi equals this. So we know these very well. And we know from my first lecture that you all remember that the Electroweak sector has 4 free parameters. The fourth one would be MH. So I can take these parameters as I like and use the relationships among them. So MW squared is predicted in the standard model in terms of the input parameters. So a little bit of algebra, and I get the theory prediction is 80.94. And at first glance, that looks pretty good, but it's not good enough, because look at the errors here. So if I just calculate this stuff to tree level, it doesn't work. I've got to use my radiative corrections. Okay. So we can calculate MW at one loop. So G Fermi, this is the same relationship as I had in the previous slide. Sine squared theta w is 1 minus mw squared over mz squared, and I was just too lazy to write out the previous slide. But I can shove all of the radiative corrections into this thing 1 minus delta r. So delta r is a physical thing. It's gauge invariant. It just is where I shoved all the radiative corrections there. So the radiative corrections to G Fermi, they have corrections not only from the 2-point function of the W, but they have corrections from box diagrams, triangle diagrams. There are a lot of pieces that go into the corrections to G Fermi. It's not just the renormalization of the 2-point functions. But all these things can be calculated. And at one loop, the contribution from the Higgs, again, here's the logarithm that I was advertising before. So the contribution up here from the Higgs is logarithmic, and the contribution from the top quark is quadratic, mt squared. Okay, so in general, the quadratic dependence on the top mass and the logarithmic dependence on the Higgs mass. And again, you need all the contributions to delta R. Yes?
This is maybe an obvious question, but is that delta RT corresponding to diagrams where there's a top in the loop? Is that how we should think about that?
Yes. So let's obsess about this plot a little bit to see that we really understand it. You've all seen this plot, I'm sure, many, many times. But it's actually a plot that conveys a lot of information. So here's the top quark mass. The yellow is the measured value of the top quark mass with the uncertainty bands. The yellow here is the measured value of MW with the uncertainty bands. So we can do a fit to all of our data, all of our Electroweak precision data. And what does that include? That includes the very precise measurements from LEP of Z to 2 fermions. It includes the W boson width. It includes the W boson mass. So it includes the whole spectrum of measurements we have. And we'll fit to these measurements by letting MW and MT float. So everything else will be fixed, but we'll let MW and MT float, and we'll extract the best theoretical value of MW and MT, and that's this blue thing right here. So this is our prediction of where MW and MT would be from radiative corrections. And you can see that the W mass experimentally is a little bit higher than the fit here. The other interesting thing from this plot is that suppose we had a different Higgs mass. This blue has our 125 GeV Higgs mass. Suppose we had a Higgs mass that was say 300 GeV. This blue thing would just be shifted over to this line here, okay? And if we had a 600 GeV Higgs, it would be shifted over here. So before the Higgs discovery, you would see these bands depending on where you thought the Higgs mass was. So it's actually kind of impressive that the Higgs mass fits the data so well. Okay, so what is this going to tell us about anything? I have this comment here about CDF. So let's keep going with our theme to try to learn about Higgs physics from radiative corrections. Well, the 2-point functions can be categorized in terms of things we call S, T, and U. And I wrote down the formulas here just for kicks. And they're just really the 2-point function of the Z. So here's the S parameter. It's essentially the running of the ZZ 2-point function from MZ to 0. So that's the basic contribution to the 2-point function. Delta T, so these first two terms you see are really what I call the rho parameter. So alpha T is exactly the rho parameter. It's just new nomenclature. And U here is the running of the W from 0 to MW squared and the running of the Z from 0 to MZ squared. So it's the running of the parameters. Most of the things that we measure don't depend on U other than MW. So you can calculate the 2-point functions for your theory and then see what they do. And then you can predict, for example, MW squared in terms of these guys. This is an approximation. This is not the full calculation of radiative corrections to the W mass. This is saying only the oblique parameters contribute. So how do the oblique parameters contribute? Well, minus S plus T plus U here. And so if you're enthusiastic and you take all of these things, put it in here, you won't get MW. Okay? Does anybody know why? Any comments? And the reason it's worked out in gory detail here. The reason you won't get it is because this piece also gets contributions from the 2-point function. So if I predict MW, let's go back. Yeah, we can go back here. So I'll predict MW from this kind of relationship. But alpha, for example, will get contributions from pi, gamma, gamma, and so forth. So you've got to renormalize the input parameters too. But since this isn't a course in radiative corrections, I'll just tell you that this is the answer. So suppose I wanted to increase the W mass. This tells me how to do it, right? This tells me that I need a theory which has negative S, positive T, and positive U. So the first approximation, I can look for that kind of theory. And I will show you some examples of how you can use this kind of logic to really learn about new physics. Yeah, good.
Is there a reason why W and Y aren't included in this, aside from the fact that they're small in those models, since they're also dimension 6?
It's just laziness. They're smaller. I could put them in, yes. And in fact, this paper here puts them in, but typically they're very small.
So it looks like, I mean, it seems like you're capturing loop effects in both these oblique parameters and in this MW squared of SM. So I guess I'm not really understanding the utility of ST anyway.
Well, it's a quick and easy way to estimate the effects of new physics. And some new physics only comes in via these parameters. So, for example, the Higgs, if I'm calculating the corrections to muon decay, which is G Fermi. So the corrections to muon decay, there's a mu, a neutrino, W exchange, electron, neutrino. So the Higgs only talks to that W. So it only contributes to these 2-point functions. So that makes it very useful. On the other hand, if I had some model where there was some Z prime that connected from the electron to the muon in a box diagram, then this formalism wouldn't apply. There would be further corrections. So it's just a quick and easy way of estimating the effects of these higher order corrections. And a lot of times you can think about your model, draw some pictures of how it would contribute, and say, aha, all the contributions are from the 2-point functions. Yeah. I mean, if you're building a model, it's the first thing you check. You should calculate the 2-point functions, and then you look at the G-fitter plots for S and T, and then you put S and T on their plots and say, aha, my model's screwed up, doesn't work. Back to square zero. I mean, and then you might do the real radiative corrections if you have some model where everything works. Renormalized, right? There's no issue. It's straightforward. It's just that there's more than just plugging this stuff in. You have to renormalize the input parameters too to get this formula. What's the renormalization scale? Probably MW. I mean, for these guys, it's fixed, right? It's MZ, 0, so forth. And here, it's going to be higher order, so the difference between scales won't make any change. So let's use this stuff. Let's do something useful. Let's learn about some new physics. I gave you the example of the rho parameter calculating this loop with the Higgs. Well, now the rho parameter is MW squared over MZ squared cos squared theta W. So in general, you know where the MW comes from. It comes from the gauge invariant couplings of the gauge bosons to the new Higgs particles. So you know that it's V squared here. This thing up here is MW squared. It's the SU2 invariant, SU2 plus 1 minus a quarter Y squared. This thing down here is MZ squared cos squared theta W, and it's a little bit more complicated, but it's just Y squared V squared. In fact, in a previous TASE, Heather worked it out, took 10 pages to work it out, got every minus sign there. So the trick in working out the denominator is actually you're calculating MZ cos squared theta W, so you've got the Z mass in terms of the gauge generators giving it. But now you're operating on a Higgs field which has charge 0. So what she does is she turns the T's into Y's by saying 0 equals T plus Y. So they're equal and opposite for this. So this is a very powerful formula here because this tells us what the rho parameter is in various scalar sectors. So let's think about an SU2 doublet. That's a standard model. For an SU2 doublet, y is 1. So you can write q equals T3 plus y. That tells you y is, let's see. Is that right? Y is 1. Yeah. So down here, here's an SU2 doublet. So T is a half for a doublet. So there's a half. Half plus 1 is 3 halves. Minus a quarter y squared. That's a quarter here. V squared. And downstairs, it's a half y squared v squared. So you get 1. So no matter how many doublets I add, I always get rho equals 1. And this is cool for model builders because the rho parameter is really stringently measured. It gives us the most limits on our models. So this says, well, let's add 2 doublets. Let's add 3 doublets. Hell, let's add 4 doublets. Go ahead and build your model. You can add doublets as you like. So that's cool. I mean, people have made models where each generation has its own Higgs, for example. So the first generation has one Higgs, second generation has another Higgs, third generation has another one. 2 Higgs doublet models are popular. But all of them, you don't get in trouble with the rho parameters. So these are very nice models. What about if you had a gauge singlet? A gauge singlet doesn't contribute to MW and MZ because it's a gauge singlet, so rho is 1 trivially. So people like gauge singlets too because they don't mess up the rho parameter. But what about triplet scalars? That's the next simplest thing. Well, we can use this formula to get the rho parameter. So there are 2 possibilities for Higgs triplets. There's a y equals 0, which has plus 0 and minus, and there's a y equals 1, which has doubly charged scalars, singly charged scalars, and neutral scalars. Okay, so we can go back. We can take our formula here, t plus 1 minus a quarter y squared, put in the y equals 0 and the t's for these guys, and calculate the rho parameter. So here's the rho parameter, and it's particularly interesting. It's the VEV of the y equals 0 squared guy, and it's minus the VEV of this guy. So if I have triplets, the sign, SIGN, of the contribution to the rho parameter is fixed, regardless of the parameters and regardless of the size of these v's and so forth. So that's kind of interesting. So if I have the y equals 1, the rho parameter is negative, and if I have the y equals 0, the rho parameter is positive. So let's go back. Okay, here we go. We want to make the W mass bigger to explain the fact that CDF has a slightly bigger W mass than we thought. So we need to have, what? When you do a global, that's irrelevant, Tom. Tom, that's a stupid question. It doesn't matter. It doesn't matter. It feeds into the global fits. So the point is, if you want to make the W mass bigger, you can make T bigger, okay? So you want to make T bigger, you can pick a triplet y equals 0. So this is how the model building goes. And it's sociologically amusing that, you know, there are an infinite number of papers that came out on this. And one of the first ones got the sign wrong here and put in the y equals 1 triplet by one of our colleagues. So that's kind of funny. But it's fixed. You can have this guy, but you can't have this guy if you want to increase the W mass. So in your model building, you can kind of explore the features you want to have. Yeah?
Because in principle, it seems like we don't require VEVs.
Yeah, sure. No, you don't have to have them have a VEV. You know, you can do all the symmetry breaking with the SU2 doublet. Yeah, no. But of course, if you don't have, well, you have to arrange your let me put it this way. You have to arrange your parameters in your potential so that these guys are heavy, right? And I won't say you can't do it without having a VEV, but I suspect you would have to have strong coupling or something. Okay, so are there questions before I move on to the Higgs mass? Okay, so the Higgs mass, it's measured extremely precisely. Here is the the world average here. It's 125 plus or minus 0.24. So we really know what the Higgs mass is. But as I said, it's not predicted in the standard model. It's a free parameter. It could have been anything. So does this tell us anything? We know the mass. What's it mean? Can we learn any new physics from it? So let's try to learn something from the measurement of the Higgs mass. So I remind you that the quartic term in the potential, h to the fourth, is mh squared over 8v squared h to the fourth. So lambda is just the coefficient of h to the fourth over 4. And the reason I wrote that down is because sometimes in the literature, people normalize this term differently. Doesn't matter how you normalize it. This is my definition of lambda. Okay, so we got lambda, and we know that lambda is really mh squared over 2v squared. Good. So we know that in quantum field theories, everything runs, right? We're not fixed. So let's try to calculate how these couplings run. So here's lambda. Here's HH, and here's the tree level piece, minus 6i lambda. So then I can calculate the contributions of loops to this, H. So this is a top quark loop, and there's 6 symmetric permutations of the external Higgs. There are other contributions to the lambda running. So I could have loops with scalars inside, and that's a fun exercise to calculate all the diagrams with 4 external scalars and scalars inside. I could have the 4 external scalars and some gauge bosons inside. So this is just a piece of the picture to show you how it goes. But it's fun to calculate. So I can calculate the loop corrections for the 4 external scalars here. And what do I get? I get a factor of 3 because the top is colored. The couplings of the top to the Higgs I call GT here, so 1, 2, 3, 4, so there are 4 of them. And then I just do this integral, so it's trace k plus m, k plus p1 plus m, k plus p1 plus p2 plus m, and so forth. So one can just do this, and I'm just pulling out the pole. So there are a bunch of finite terms, which are complicated and so forth. I don't care about the finite terms. There's a pole, 24 over epsilon. And I claim I got the factor right. So how does the quantum field theory work? Well, I just renormalize the parameters to get rid of the infinities, to absorb them in the definition of the renormalized parameter. So the renormalized coupling, which I call R, now depends on a scale. That's this arbitrary scale here, mu. Okay? And it's minus 3 gt to the fourth, and then there's a log of mu. Because I can expand mu squared to the epsilon is 1 plus epsilon log mu squared. Yes?
Maybe a stupid question, but is there an e to the minus Euler gamma there?
Yeah, that's finite.
Okay.
Yeah, absolutely. There are a bunch of finite terms. There's a gamma 1 plus epsilon. Yep. But I'm only interested in this log mu squared piece. That's why I calculated the 1 over epsilon. So I've got the running of lambda. So let's look at what this does. What that says is that if I take mu big, as I push mu up, it pushes lambda negative. So the quartic coupling is pushed to be negative at high scales. So it runs, and it runs pretty quickly because GT is the coupling of the top to the Higgs, so it's actually MT over V. So let's see what that does. I can look at how the quartic coupling runs. This is called the renormalization group scaling. So here's d lambda d log mu squared here, 16 pi squared. Here's the term I calculated, minus 12 gt to the fourth. Hopefully I have all my factors right. So the top quark loop has a minus sign. So this 12 lambda squared is from calculating the contributions with all the scalars running around. So this guy is positive. So there's a playoff between these two terms because they have opposite signs. So if lambda is small, say a light Higgs, remember it's mh squared over 2v squared, the coupling to the top quark here causes lambda to become negative, okay? Whereas if lambda had been heavy, if the Higgs mass had been very big for this term to dominate, the lambda would grow with scale. So we have to have both effects here. And so let's see what this means. Okay. So here you go. You can calculate the running of lambda. And this particular plot here is, I don't know how many loops. It's got the most loops that anybody's ever calculated. But the physics is exactly the same. So a negative lambda would make the potential be unbounded from below. Okay? So as lambda goes to 0 here, and I lose the, as I lose the quartic coupling, if lambda is 0, it's a non-interacting theory. So here we have the Higgs quartic coupling, and you see it running out to the scale here, and this GT to the fourth term is pushing it negative. And one thing you see from this plot is it's excruciatingly sensitive to the exact value of the top mass. So here's the top mass of 171, here's the top mass of 175, here's the top mass from the PDG of 172, and you can see it looks like lambda is being pushed negative somewhere around here, being pushed negative before I get to the Planck scale. Yes?
Is a negative lambda consistent with a physical theory?
No. Right, because, well, I have it on the next slide. A negative lambda would go, potential would go like this. Yeah, no can do. So this is a problem for our theory, that lambda is being pushed negative. But on the other hand, you can say, yeah, way up there. So what does this actually mean? Okay, so what it means is that the Higgs mass is very finely tuned. So here we have the Higgs mass and the top mass. So here is the unstable where we're up here, and here's our potential, and it's going to roll down. Here's what we really want to be, is to be at the bottom of the potential. And you can see that to be in a stable universe where we're always at the minimum of the potential, here's the 125 GeV Higgs. And you go up here, and the top mass would have to be sort of 171 or so. So it looks like we're up in this metastable region. So the Higgs mass is telling us something about the universe, that maybe we're not in a stable universe, but rather we're in a metastable universe. So again, we need to keep calculating things like this to see what they imply, because every time we get a new measurement of the top quark mass, alpha S, the Higgs mass, we move around on this plane a little bit. But nonetheless, you can see that something is happening, you know, right around the parameters that we have chosen. So the 172 GeV top mass and the 125 GeV Higgs mass, the answer to my question here is, yeah, it is kind of weird, because we're right here in this funny region. We're not stable, we're not unstable, we're just kind of in this funny region. Yes?
How do you actually calculate this plot? I've never seen.
Oh, okay. So you would say that here you would be unstable because the potential is turning over, for example.
Sorry, how are you defining metastable?
How do they define metastable there? Well, what that means is that you're not in the true vacuum of the theory. But the lifetime before I tunnel out of this vacuum to the true vacuum is longer than the age of the universe.
Okay.
Yeah. So to me, it just says that we're in a very special region of parameter space, just on the edge. Yeah?
So the fact that we're in a metastable universe means that any time there's some small probability the vacuum could tunnel to 0, right?
Well, it's pretty small.
Which would mean that all of the standard model would lose mass.
Well, in this universe, it's longer than the age of the universe.
Sure.
So in this region. Yeah, what does it mean? I don't know.
Right.
Yeah, right. I mean,
I always wonder why people are not more concerned about this.
well, I think people who do cosmology and so forth are concerned about this. Yeah. Yeah, right, right, okay. So, all right, yeah?
A question about the top mass, because the top mass that experiments measure are not the direct top mass.
Yes, this is a perennial question. Let me rephrase the question for people who, let's see here. Okay, this top quark mass here is a top quark mass that's extracted from experiment. Theorists tend to use MS bar when they do calculations, so you have to very carefully match between MS bar and what they extract. Right, so what I'm going to tell you is that they did it properly in that plot. They took what the experiments measured and translated it into an MS bar mass. Yeah, but yes, there is a difference between the two, and you have to be very careful. And there are some theoretical uncertainty associated with that. Yes?
Would it be correct to assume that the bombshell masses they are providing, EDG?
Yes. Okay, so what else do we have as problems with the Higgs? So the question is, do scalar fields make sense? Okay, so let's think about how fermions and scalars are different. Suppose I go back to my U1 abelian theory that I had on the first day. So I've just got a Lagrangian, which has a fermion psi bar d slash psi. It's got d mu phi squared. I'll put in a mass term for phi squared, and then I'll put in a Yukawa-like interaction. So this is a simple way of looking at the standard model. So this theory, I'll just assume phi has a vev here, and the mass of the fermion is then lambda f times v. Okay? So this is a mock-up of the standard model, just for simplicity. So I can calculate the mass renormalization of the fermion. It's easy. Here's my fermion. Here's my Higgs. I can just calculate this two-point function here. There's a lambda f at both vertices. There's a k slash plus m here. And then there are the two propagators, fermion propagator, scalar propagator. So now I'm going to calculate this mass renormalization using a cutoff. And now most of you probably always use dim-rag, right? But if you want to do it with a cutoff, you're free to do the calculation with a cutoff. And in fact, in the backup, I provided the formulas you need to go from here to here. So I'm going to do this d4k integral, cutting off the integral at some scale lambda squared. And when I do that, what do I get? I get the mass, the renormalization of the mass of the fermion is the mass of the fermion times a logarithm, plus a bunch of other stuff I don't care about. So all I care about is the mass of the logarithm. So the fermion mass renormalization is logarithmic. So it's also proportional to the mass of the fermion. So if the mass of the fermion is 0, these quantum corrections vanish. And so in this case, the Lagrangian's actually invariant under phase transitions of the left-handed guys and the right-handed guys. So setting the mass of the fermion to 0 increases the symmetry of the theory. The Yukawa coupling, which is proportional to the mass, breaks this symmetry, and so the corrections are proportional to the mass of the fermion. So this is a nice picture. We understand the renormalization of the mass of the fermion. It's logarithmic. But now let's think about the Higgs, the scalars. Let's just do the same calculation, calculating the Higgs with a fermion loop. Same simple theory, got the same vertices here, and then the trace here of k plus m, k minus p plus m, same propagators, no swindle here. I'll integrate this with a cutoff using my notes in the backup, should I want to. But what happens is that the renormalization of the Higgs mass is proportional to lambda squared. It has a quadratic sensitivity to the high-scale physics. So back in the old days, we used to say that there was a quadratic divergence, but now we understand that a better way to phrase this is that if I cut off the theory, it has a quadratic sensitivity to the new physics at the UV scale. Okay, so here we go. And that makes sense because there's no symmetry that protects the Higgs mass, whereas the fermion mass, there was a symmetry that protected it, that made it proportional to the mass and logarithmic. But here I have this lambda squared. And this is the simplest way of explaining what we call the naturalness problem. The naturalness problem is that if I calculate corrections to the Higgs scalar mass, they're quadratically sensitive to whatever's going on up at the high scale. Yeah?
Are there any kind of symmetries you could?
Yeah, I'm getting there. Right, so this kind of thing is kind of uncomfortable. It's not that it's bad or that there's any problem or anything. It's just that it makes us think about, well, there's some new physics up there that's going to explain dark matter or whatever. I don't know what it is, but somehow my Higgs mass is quadratically sensitive to it. So I can expand the Higgs sector. I can add a bunch of stuff to it. So let's add some gauge bosons, V mu. Let's add some scalars, S dagger S. Let's add some fermions. So L bar, L, those are random new fermions where this is a doublet and this is a singlet. All of these are gauge invariant terms that I can add. So if I just do these simple calculations again, what do I get? I get a contribution from the gauge bosons, which is positive. I get a contribution from the scalars, which is positive, and I get a contribution from the fermions, which is negative. So aha, you say. We can try to cancel these by having the proper spectrum of new physics in our model. So if I had a theory where I had scalars and fermions that had exactly the same mass and roughly the same couplings, aha, bingo, this would cancel. So now you all know the entire motivation for 3,000 papers on supersymmetry. Because in supersymmetry, all of our known fermions have scalar partners, which we thought in the beginning maybe they weren't too heavy, so you could have this cancellation just happen naturally, and that would be very beautiful. Okay, so you could also try to arrange it with the gauge bosons, but that's harder, yeah?
Going back to your point about the naturalness problem, why is the naturalness problem a problem?
It makes us uncomfortable to think that we're getting these large corrections to the Higgs boson mass that then we have to adjust in perturbation theory. Big corrections make physicists uncomfortable. We like to understand where corrections are coming from. So we don't mind these logarithmic corrections. Logarithms go slowly, and we understand exactly the structure. But stuff like this makes us uncomfortable. It's not a problem per se. It's perfectly acceptable, but it makes us uncomfortable. So you could say issue. But we always call it the naturalness problem. And it's just the sensitivity. Okay. So that leads us to think, well, everything isn't perfect in the standard model. Let's go ahead and see what happens if we add more Higgs bosons to our theory. We don't have any reason to expect there's just one. So maybe we can solve this problem, as I was saying, with the cancellation, like in supersymmetry. Maybe we can solve it with some cancellation, in higher dimensional models, whatever. So the simplest possibility is to add a singlet or a doublet. I mean, there are lots of possibilities, but these are the simplest, and they kind of illustrate the points. So let's add a singlet scalar. I showed you that a singlet scalar doesn't contribute to the row parameter, so it doesn't do much to radiative corrections, so it's relatively benign in terms of stuff I can add to my model. So my singlet scalar is going to be S. It's going to be invariant under a Z2 symmetry. S goes to minus S, and that means that there are no cubic terms in the interaction potential. So I've got my standard model potential, mu squared, phi squared, lambda phi to the fourth. Then I've got a mass term for the S as a singlet, so I can add this. And then I've got an interesting mixing term between the SU2 doublet and the singlet. And then I've got a quartic term in the singlet. So this is a pretty simple model. And so when S gets a VEV and when phi gets a VEV, the fields mix, and the physical fields, which I'll call little h and big H. So big H is the new guy, and little h is the standard model. They mix by some mixing angle. So you get a 2 by 2 matrix, and you diagonalize. So you get a mixing angle, cos theta times the Higgs minus sine theta times the S. Okay, so what are the physical parameters here? Well, we started out with 1, 2, 3, 4, 5 parameters there. So we've got 5 parameters, which we can take to be MH equals 125, the heavier Higgs, the VEV of the SU2 doublet, tangent beta, which is the ratio of the VEVs of the SU2 doublet to the singlet, and this mixing angle theta. So tan beta here is not the tan beta you might know and love from the 2HEM, but it's the ratio of VEVs. So this new scalar is particularly interesting because it's a gauge singlet, and it only talks here to the scalar sector. So this is what we call a Higgs portal model, because we've got this S, it talks to our SU2 doublet scalar, then it mixes, and that way it talks to the standard model. So it talks to the standard model through this mixing. Yeah?
Does that singlet have to have a VEV? I mean, I see that you would get a divergence if it were 0.
Well, it automatically gets a VEV. We'll assume it's spontaneously broken.
Okay.
Yeah. Okay, so this is a Higgs portal type model. So it's a very, very simple model, but nonetheless, we can learn something from it. So the couplings to the standard model particles are just cos theta, and the couplings to the heavier Higgs are just sine theta. So all these kappa measurements I was talking about in the last few days are really just a measurement in this theory of cos theta, measurement of the strength of the couplings of the fermions and gauge bosons to the Higgs. But in this model, if it's kinematically allowed, you could have this heavier guy goes to 2 of the standard model Higgses. So you can get some new phenomenology from here. So the width of the standard model Higgs is just co-squared times the standard model. And the width of the heavier guy is sine squared times the standard model width of the Higgs, plus the decay width from a heavy Higgs to 2 lighter Higgs. Okay, so there are experimental limits on this coupling suppression just by looking at the mu parameter for H goes to fermions. And right now it's about 0.12. But as I say, it's a moving target. As the Higgs searches improve, this limit gets better and better. So you can also look at information from recasting heavy Higgs searches. And what do I mean by that? At the LHC, they look for heavy Higgs, say 600 GeV, 800 GeV, decaying to W bosons. So there are a lot of limits on heavy Higgs going to W bosons. So you can take those limits and just reinterpret the couplings in terms of this model. So that's what I mean by recasting them. Okay, so let me just show you the kinds of limits you get. So this is part of our procedure for looking at new models. So we get restrictions from precision electroweak measurements at LEP. So this is the ST and U parameters I was talking about, doing the radiative corrections properly for all these precision electroweak measurements. So this will tell us something. This is, let's see, this blue line here about the mass of the heavy guy in this mixing angle. So check 1, we checked off electroweak precision observables. We can do a global fit to electroweak precision observables plus Higgs decay plus dibosons. And that's, let's see, that's the black one. Or we can just look at single Higgs production, and that's the solid line here. So we've got these 3 different ways of looking for limits on these models. And if the heavier guy is relatively light, you can see that the best limit is from Higgs couplings, whereas if the heavier guy is, say, a TeV, the better limits would be from these global fits. So it's particularly interesting. I was talking about the W mass as a proxy for looking for new physics. So if I look in this model, I see that the red line here is the limit from the W mass. And you can see that you get very, very good limits for heavy Higgses from the W mass on the parameters of this theory. Yeah?
How much do these limits change if you want to believe the new W mass?
Oh, yeah. I'll tell you this. You don't have to ask. So we can, of course, compute the contributions of the new scalar in the singlet model, following our theory where we did it before. We saw for triplets you could distinguish between isospin 0 and isospin 1 triplet VEV. So here let's just do it for the new Higgs boson in this singlet model. So I can calculate the contributions to S and T here from this new singlet. So here we go, the contributions to S. It's logarithmic. Here's the heavy mass, and here's the standard model mass, because we always calculate relative to the standard model. So when I say delta S, what I mean is I calculate S with all the standard model contributions, then I subtract that off of what I'm calculating in my new physics model. So delta S is the difference from the standard model due to my new physics. So here's delta T. So here's delta T. The sign, SIGN, is fixed, and it's log mh squared, the heavy guy, over the standard model guy. So this guy is negative. So in this model, the W mass is pushed to be smaller than in the standard model. It wants to have the W mass lighter than in the standard model. So the fact that already our W mass is above what the fit says that it makes the electroweak fit worse than in the standard model. So you cannot increase the W mass with this. You're always decreasing it. So the Higgs physics is telling you that in this class of theories, your W mass is going to want to be smaller than in the standard model. So this is a fit which has a new CDF MW. So I should be clear, it doesn't take the value of MW from the CDF fit, but it averages over the world average. There are a whole bunch of measurements and comes up with a new value. And I don't know why these guys do it, but they plot MT on the y-axis and MW on the x-axis as opposed to G-fitter, and this is just to confuse you. I mean, you got to stare at it. But, okay, so here we go. We see that the W mass is a little bit off. Here's the fit, and here's the measured value. Okay, so the singlet model makes the fit worse, and we get this from these very, very simple arguments. So that's kind of fun. So that goes back to explain why when the Higgs is heavy, here's the red line, you get the best limits from the W mass because it pushes it away from what we know we have to have. Okay, so this was kind of for fun, showing how you can learn new things just from putting scalars into radiative corrections. So a lot of things happen in this simple singlet model. For example, since I have two Higgses now, H is the standard model guy and big H is the new Higgs, I now have couplings which look like H cubed, which I have in the standard model, and I have couplings which couple two standard model Higgses to one new Higgs. So I can get lots of new information about this. For example, here are the couplings written in terms of these cos squared and sine squared. So this is a standard model guy. So if cos theta is 1, you get the standard model result back. Okay, so that's good. So here's the coupling to the heavier guy. Okay, so here it is, mh squared sine squared theta. But it has this funny feature that there's a contribution which grows with the mass squared of the heavy guy. So you should all remember from unitarity. Unitarity tells me that the partial waves have to be less than a half. And if you have something which is growing with mh squared, bingo, right? You make mh squared big enough, you're going to violate the unitarity bound, ergo you got a limit on the theory. So this is part of our repertoire for learning about these theories. And in particular, if you calculate all the contributions to HH, goes to HH. There are more diagrams in this, by the way. You get a limit on this tan beta, and you get a limit on MH. So tan squared beta times MH squared can't be too big in this model. So if you try to take your heavier singlet Higgs, very, very heavy, then you're going to have to take this ratio of EVs to be very, very small to conserve unitarity. Okay, yeah?
So the singlet model, the MW mass goes low, but the rho parameter stays the same.
Yes, because it's a singlet, so it doesn't contribute to the W and Z masses. Exactly. That's a good question. So the rho parameter is still 1. Yeah.
But then it brings down the MW mass.
Yeah. Yeah. Yeah?
How does like adding either a new singlet or a doublet like help solve the naturalness problem?
This one doesn't do spit for it.
Okay.
Exactly. Absolutely nothing. Yeah. But the doublet one does, because I'll go ahead since I might get to the doublet. The 2 Higgs doublet sector is the scalar sector of the simplest supersymmetric model. So in that sense, it's part of the, could be part of the picture. Yeah. But the singlet, no, does nothing. It gives you a lot of cool new phenomenology, a playground to look for new physics. It's quite simple, and it's motivated because you think it might be a portal to something else. Okay, so there are a lot of kind of cool things that happen here. You can have the branching ratio of this heavier guy to the standard model Higgses be actually pretty big. So you can see here the branching ratio could be, 0.4, 0.3, whatever. So you can have fairly large branching ratios of the heavier guy into the lighter guys. And what does that mean? That means that I can have, instead of glue goes to Higgs standard model, goes to 2 Higgses, like we were talking about for double Higgs production in the standard model, I can also have a contribution from this heavier Higgs. So I can have the 2 gluons make the heavier Higgs, and then it makes the 2 lighter Higgses. So I have an extra contribution to double Higgs production, which is another motivation for this kind of model. And in particular, in the models with extra singlets, we can have the case where instead of making 2 standard model Higgses, I could make 1 standard model Higgs and 1 heavy Higgs. So I could make 2 Higgses, but they would be different. I could produce the 2 different Higgses of this model. So you can see how people who do BSM think this is pretty cool. So what these guys did, this was a snow mass plot that I kind of like. They said, how big can I make the 2 Higgs signal by playing around with all the parameters? How big can I make it relative to the standard model? And you can see that they can't make it that much bigger. I mean, you can have, so this is the ratio in their particular model of the biggest possible branching ratio to make 2 different Higgses. So it's not 0, but it's not infinite. So here's the plot that probably my slide should be ordered in the other way. So you're making two Higgses. You could have the heavy guy, you can have the light guy, you can have the two guys here. So now these two different scalars can interfere, and you can have resonance effects, right? So you can have a resonance from this guy, you can have a resonance from this guy, and then you can have the interference between the two when I calculate the whole thing and square it. And so what happens is that you get large bump dip patterns. You get resonance interferences have a classic pattern. So let's pick one of these lines here. Let's say the heavier guy was 300 GeV. So that's this blue guy here. So here's below the 200 GeV resonance, and that bump, dip, and then it asymptotes here. So this bump dip pattern is from the interference between the two resonances. Yeah?
How should we be interpreting the y-axis here?
Oh, this is just the ratio to the standard model. So here's my singlet model, and it's a ratio to the standard model. So you see, that's actually an interesting point. So you see that it's maybe 10 times bigger than the standard model in some regions, and then out here, it asymptotes to the standard model. And this is in terms of the invariant mass of the two standard model Higgses. So that's one of the points of this model, which is my next slide, is that in models like this, you can really enhance the rate for making two Higgs bosons. So all the LHC experiments right now are focused on finding two Higgs bosons. They haven't seen them, and they're really hot to see these two Higgs bosons. So models like this could give a fairly big enhancement. So that's kind of an optimistic scenario that, maybe it's new physics. So, for example, here is the ratio of the singlet to the standard model for making two Higgses for various parameters. And you can see for this set of parameters up here, the enhancement could be a factor of 20 over the standard model, which is actually ruled out since I showed you a couple days ago that the limit was now 6. So we're down here, but you could still have an enhancement for perfectly reasonable values of the parameters of the theory. You could see more Higgses, or more double Higgs than you thought. So this leads me to how you analyze and study these models. This is a plot that was made for the European strategy study, and it really illustrates how you look at models like this. Because you've got your new model, it's got couplings to the standard model Higgs, which are going to give me some limits, but it's got this heavier Higgs, which I also want to look for. So let's pick one of these machines. This has every machine under the universe. Let's pick, let's see, how about the high-Lumi LHC? So the high-Lumi LHC is going to measure the Higgs couplings. So here it is. It doesn't depend on the mass of the heavy guy. It's just a straight line going across. So it's trying to measure these Higgs couplings to about, let's see here, this is 0.02 or something, 2%. So this is a 2% measurement, which somebody thinks they can get. So you can also look for these heavier Higgses, okay? So here, depending, let's see, it's this line, this black line here, okay? So depending on the mass of the heavier Higgs, in some regime, you're more sensitive to the couplings by looking at the heavier Higgses. Okay, down here, you're way sensitive. But out here, you get it all from looking at the Higgs couplings. So what they've done is go through all these machines and looking for the regime where you're more sensitive from Higgs couplings or where you're more sensitive by directly looking for these new particles. And so we see plots like this for all the models that we're making, the Higgs couplings versus the direct searches. But that model was kind of simple. Let's make it more complicated because it gets more interesting. We put in a Z2 symmetry by hand. Let's take out the Z2 symmetry. Let's add in terms which are odd under S goes to minus S. So you can have a single term here, and an S cubed term here. So you can have 3 more terms. So again, you can just go through your potential. But the interesting thing here is I've added all the terms. Let's look at this. All the terms which are allowed by symmetries. There are no missing terms. So if I minimize my potential and I got a VEV of S, which was, I don't know, whatever it is, I could get rid of it by redefining my potentials, or by redefining my parameters. So I could just shift the B's and the S's. I can just shift everything to get rid of the VEV. So it's consistent to take the VEV the VEV of S equal to 0 here because I can just redefine the parameters to absorb it. So that's kind of nice. So when I look at these Z2 violating symmetries, theories, I don't have a VEV. I can define it away. So the terms that I have are A1, B1, B3. So I've got more terms that don't mean anything. But you can still study what happens in terms of the mass of the heavy guy, the couplings of the Higgs, the couplings of the heavy Higgs to double Higgs, and so forth. And what you get, just a second, what you get here is di-Higgs production, again, can be enhanced even in these models by factors of, 10, whatever. So we know that it can't, experimentally, it's within a factor of 6. 1, 2, 3, 4, 5, 6. So you can still get very significant enhancements of di-Higgs production, even with relatively light scalars. Yes?
You said some of those parameters don't matter.
I didn't say that.
Or maybe I misheard you.
Yeah, you got all these parameters. They're there.
I think you said that the A1, B1, and B3.
They're all there. You have to go through. I mean, you play your game. You got your potential. You diagonalize a Higgs mass matrix. You get your physical couplings, and they depend on 7 parameters in this particular thing, which you pick your 7 parameters as you like. I like to pick masses and mixings, but we're left over with, say, B3 is still there, B4 is still there. And you can limit these guys by, anybody? Unitarity, right? You can do the unitarity constraints here and see that these parameters, for example, B4 has to be less than 4 or something. Yeah, but yeah, they're there. But you can still get information out, is my point. You can get information, for example, that di-Higgs production is significantly enhanced, even in this model. Okay. I'm going to end with a simple example here because this is going to lead into talking tomorrow about SMEFT. Because in this model, it's a simple model, and we have extra Higgs singlet and some extra parameters in my potential. But what if I set the mass of this new guy to 100,000? I took its limit very high. Then what would it do to my theory at low energies? So suppose the gauge singlet S was very massive, and here's phi. It's, as always, is our standard model like scalar doublet. So here's my theory. It's got the kinetic energy for my new scalar. It's got a mass for the new scalar. It's got this very interesting term which couples the SU2 doublet to S. It's got this term which mixes phi squared and S squared, which is a very interesting term. There's no Z2 symmetry, so there's an S cubed term, and there's an S to the 4th term. So I can integrate out S using the equations of motion. This is called the covariant derivative expansion. So I just take dl ds, and I'm going to set it equal to 0, assuming that the mass of the scalar is very large. So I'll start by writing this potential in a way that makes this easy. So here's my a squared phi squared term. I'll integrate by parts to write this term here as S minus a half d mu with S. So here's my quadratic term, minus ms squared over 2 minus kappa phi squared over 2. And then I'll assume that the higher order terms are small. So I haven't swindled you yet. Yeah, it's hard to see, right? Okay? So now I'll take dl ds, and I'll set it equal to 0 to get the classical solution. So the classical solution, just by doing that simple thing, a squared phi squared d squared ms squared kappa phi squared. So I'm going to assume the mass of my new scalar is very, very heavy because I'm trying to integrate it out of the theory. So it's 1 over the mass, the scalar squared, a phi squared, and then I've got a term 1 over m to the 4th, and then I've got this kind of interaction. So here's my classical solution for the S field. So now I can just do some simple algebra, substitute it back into the Lagrangian, and see what happens in this limit. So it's a mess of algebra, but it's algebra. It's nothing deep. So my Lagrangian is a phi squared SC, so the classical solution here. So I'm solving back in, and then I'm doing my multiplication. And what comes out? You get a modification of the Higgs quartic term, a squared over 2 times the mass so the scalar squared, and you generate new operators. So in the singlet model, setting the singlet mass to infinity, you generate operators which go like 1 over m to the 4th, a squared. Remember, a was a phi squared s term, the mixing term. So this term, OH, is just a term with derivatives on phi, so it's kind of a funny looking term, but there it is. And it generates terms which are phi dagger phi cubed, so it's h to the 6th. So my Lagrangian has generated these extra terms due to the presence of this infinitely heavy scalar. So what does this mean? This means that when I try to integrate the scalar out of the theory to just have a low energy effective theory, the quartic coupling is shifted by a term which goes like 1 over the mass of this guy squared, which that's not too interesting. The Higgs kinetic energy is shifted because I generated a correction to the Higgs kinetic energy term here. So I shift the Higgs field so it has canonical kinetic energy. And then I generate, okay, here we go. And then I generate this term, which is phi to the 6th. So the whole idea behind using the Smith to learn about Higgs physics is that I have some vision in my head of high-scale physics. In this case, it was a singlet model. I integrate out the high-scale physics, say the singlet here, and I generate some coefficients. I don't generate all the coefficients in the world that are allowed by the gauge symmetry. In this case, I generate just a couple of them. So so I have a new theory which has some new interactions. So I'm going to stop there because this is a good stopping point before I continue tomorrow. So questions? Yes? This guy? Oh, it depends on B3 because this model has this extra parameter. So B3 is just the S cubed parameter. Right, so it's just there in your theory. Because everything is connected to everything. So, no, seriously. So if I calculate the mass of the Higgs, it's going to have terms which go like this. If I calculate the mixing angle, this guy is going to worm its way in there. So it just worms its way into the physical stuff. Yeah, because you say that's not a very good parameter. Right, yeah?
It's also coming in from the heavy Higgs to 2 light Higgs production.
Yeah, it's just worming its way into all of the couplings, yes. Yeah, back there? You, yeah. Well, they're at the end of my slides if you looked at them, but I think what I'll do tomorrow is talk about the standard model effective field theory. So if you want to ask me questions about 2 Higgs doublet models, that's great. But I think I have to pick one or the other, and I think I'll pick the Smith. Yeah?
I'm still curious about the previous question. The supersymmetry, totally good cancellation, but are there any other global symmetries we could add just even if they're contrived to?
Oh, yeah. I mean, people do neutral naturalness and various things to try to do this. There are lots of models, yeah. Which I'm not going to talk about, but maybe somebody. You do have a BSM speaker? Raman. Raman will talk for sure about neutral naturalness. Yes. Yeah.
So earlier when you were talking about how the top mass and the Higgs mass together imply that we live in some sort of metastable vacuum.
Yeah.
Is it possible from that particular calculation to make any statement about a catalyzed decay of this vacuum? In other words, what you expect the energy barrier between the metastable and some global minimum to look like? Do you know how much energy of push you would need?
I'm not the right person to ask that question. Okay, Gigi, which of the lectures should you ask that to? Tunneling from the metastable vacuum to our vacuum. Later in the... Who? Juna. Ask Juna after her lecture. She's around. She's the right person to ask that question, yeah. Okay, other questions? Okay, well then we'll break here. because I don't want to start anything new. Okay. Yeah.
Very specific question. Just it's back on slide 26.
Okay.
When we're introducing this singlet model.
Okay. Wait a second. Let me. Yes.
I just didn't understand. I thought on the previous slide we had said that it was like little, so we only had the new Scalar only talking to the Higgs. But in this next slide, it looked like it also.
Oh, but it only talks to the Higgs up there, S. But this is a good question. So S is my singlet that I put in, but it's not my physical field. My physical field are these guys
And that talks
after
to
symmetry
models.
breaking.
Okay.
So it works its way in that way.
Gotcha. Thank you.
Good question. Yeah, yeah.
I'm a little bit worried about this plot where you are showing the singlet model limits.
Yeah.
So if I fix the energy of my collider, shouldn't the limits like go like this, because the sensitivity will decrease at higher masses, right? Because I will get smaller number of.
Oh, where are we here?
It's
Yeah,
slide
yeah.
36.
Yeah.
Yeah, this
Yeah.
one. So,
So-
yeah, you're showing this EHL LSC. So let's say I fix the energy to be, let's say 14.
So, but I'm way out here. So I got higher energy, so I can make the heavier guys, but I'm not sensitive to the small couplings. So the production rate depends on both the mass and the coupling.
Yeah, why should it be constant? Like why?
Oh, this is just light Higgs production. So it's just cosquared theta. It doesn't depend on the heavy Higgs mass.
okay.
I
I
hate
think
this plot. This plot is just so super
Yeah, it's
overcomplicated. Because in some senses, it's a stupid plot. I didn't make this plot. It's because all the standard model Higgs couplings are just straight lines.
Yes.
You know, so there must be a better way to do this.
So the couplings that are really there are basically these lines.
Yeah, these are making the heavy. These
The
guys
Higgs, okay.
are making the heavy
Heavy,
Higgs.
okay.
So it says you have a heavier collider, you can make a heavier Higgs,
Exactly.
but then you get less and less sensitive to the couplings. Yeah.
I just had a question on the naturalness problem.
Yeah?
So you seem to think of it more as an issue, I guess.
Yeah.
I guess I was under the impression that, I mean, you're kind of in this paradox, right, where you need your Higgs correction to be fairly small, but you need high physics to be at a high scale, higher than what we've explored so far.
Yeah.
Right. So, I guess how could you have it be an issue and not a problem? I guess is what I'm.
Well, this is philosophical. What if I calculate the corrections to the Higgs mass in DIMRAT, reg, and I renormalize the Higgs mass? I wouldn't see this at all, right?
Okay.
So all this is saying is if there's high-scale physics, it worms its way into the Higgs mass radiative corrections.
I see.
So if I calculate, so in some model, it's going to worm its way in.
Okay. I see.
So it's really a point of view. I mean, Raman's going to tell you that this is a big problem. We need neutral naturalness to have these cancellations. And of course, he'll be right. And I'm going to tell you, maybe I don't care.
Okay.
But,
Thank you very much.
yeah.
Thanks, actually.
Oh, yeah?
I had a question about the scalar singlet contribution to the W mass.
Mm-hmm.
So you said it on the wrong side.
Yeah.
If my new singlet is lighter than the 125 GeV,
Oh, super light?
yeah, then you would flip the side, right?
Do you? Yeah, you probably do. Yeah. I'm trying to think if there's anything else that would, well, yes. Did I put it here? I have it here somewhere. Yeah, so suppose I had like a 10 GeV Higgs.
Right.
Then I would flip the sign there, but then I've got all sorts of limits on this new scalar because I could have Higgs standard model decaying to two of these guys, and there are lots of limits.
I see.
So it's different. I can't do it as naively as I've done here. So then I would have to go look at the limits on two pseudoscalars of 5 GeV or whatever. You know, yeah.
Thanks.
But it's fun. That's a good thing to do. Lots of people have done it, but it's fun, yeah.
I have a question about this too. Are there
Yeah.
models where they make theta dynamical so you can turn it off, like temperature dependent? Or?
Not that I know of.
Okay.
Yeah.
Okay. Because then you get the standard model, but maybe
Right, then you get, yeah. You
But then
could-
early in the universe.
Right,
maybe
then you
have-
start playing with early universe, and
Yeah,
it's a
yeah.
different thing.
Okay.
Right, one thing I didn't talk about in the singlet model is that you can get electroweak phase transitions in
Yeah,
certain
yeah.
regions of it.
Yeah, so that's what I was thinking.
Yeah,
So
no, you-
maybe you have this, in the early universe, but then theta for some reason gets turned off.
Yeah, you can have electroweak phase transitions for cos theta very close to 1.
Okay.
Is how it works out.
Okay, yeah, I was
Yeah.
thinking like early on you'd have it close
Yeah,
to 1 and then
absolutely,
you turn it
you
off
can do
later
it,
so that
right.
it doesn't break anything today.
Yeah, I didn't talk about that because there's only so many
Yeah.
hours in the day,
Okay.
but absolutely.
Okay,
Yeah.
thank you.
Yeah.
I was curious when you're talking about the scalar singlet without the Z2,
Uh-huh.
you're saying the motivation was because of electroweak baryogenesis? Or because of it increased baryogenesis?
No, without the Z2, it's just a nice portal model.
Okay.
You know, well,
Because somewhere on the slide it was saying baryogenesis.
did I say baryogenesis? I mean, you can get an electroweak phase transition without the Z2. And that, but what did I say? Did I say something wrong? This is what did I, motivated by desire. Okay, and typically prefer negative A1, B3 in the lighter age, yeah. And then you can find a set of parameter points where you can get the electroweak phase transition.
So why is this useful for explaining that?
Well, you can have a phase transition in this model, the electroweak phase transition.
First order phase transition in this case?
You can have the phase transition.
First order phase transition.
Yeah,
Okay.
yeah. So you can have it.
Okay.
But like I said, I didn't work through all the details here. But it's interesting because typically it wants to have the second Higgs relatively light, which is an interesting physics point. You know?
Another question about the electroweak fit. So I played around with those a little bit,
Uh-huh.
and I'm curious.
Oh, let's see. Were you on that Harvard
Yes.
ambulance chaser paper?
Yes.
I liked your icons, by the way.
Thank you. One of the things we noticed was, and clearly this has been discussed a lot in the literature before, but like I think it was the forward backward asymmetry. Like there was an
That's
anomaly
sensitive
on
too.
that.
Yeah.
And I'm curious what I don't know if you know any of the history behind that anomaly and like what the people have been thinking about like there, because I was told that it was like popular to think about that a while ago, and it no longer is. And
Well,
just kind of curious.
you have to get the right-handed Z coupling to the B's different
Okay.
to explain it. And it turns out it's real hard to build models that do that.
Okay.
So for a while, people were building models which changed the right-handed coupling of the B to the Z. But now all those models are ruled out. And so now everybody's forgetting about it.
Okay.
Yeah, so
It's just because there's no
there's no,
sensible way to do that.
well, nobody has a good model, so people have just kind of let it sit there.
Okay.
So if you have a good model, that'd be cool. Yeah.
Okay, thank you.
Yeah.
So in this slide, you says the lambda going to get some negative collection. So, prospects of the metastability is it's not good, right?
What's that? I can't hear you, sorry.
Sorry. In next slide, you said the lambda got collected to the negative values. I mean, it feels like
No. It's this one, right?
yeah, in the later slides, you said a singlet model without G2, it gets collected to negative values, negative collection
Oh, MW?
in lambda.
I don't think I said anything about lambda.
In single,
These guys?
in the latest one, in the lastest part,
Which one?
in the last slide, maybe you said that lambda become lambda minus some.
Oh, this guy?
This one.
Oh, so if I integrate out the singlet, I get a
Integrated as
correction
in-
to lambda, and I get a correction a squared over ms squared.
It doesn't mean that lambda really become a negative, right? Even
No,
if
what it
the-
means is that this is the quartic coupling. It gets us extra contribution.
Okay, so my question was if we
But
consider-
remember, we're thinking about ms goes to infinity in this. So it's just a small shift. It's there, but it's small. Because
But it is in between some, because you talked about some metastability. It is
oh no,
worse.
you would have to redo the whole calculation in
Yeah,
this
right.
theory. It would be different. Lots of
The
different.
running will be also
The running is different,
I see.
and I don't know what it is, but it would be
Okay, I
different.
cannot say just the.
No, you can't say from here. No, sorry.
Yeah,
You have to redo it.
I see.
Yeah.
The second question is of a hierarchy problem. So within the standard model, we do not have such a collection, right?
A hierarchy problem?
Purely within the standard model. We do.
Well, the hierarchy problem would say, why is MW less than the Planck scale? I don't know. So we do have a problem because it doesn't explain that.
Yeah, just a correction. So in slides, I think you didn't put error bar of top.
I didn't put what?
Error in the Quark Mass when you talked about.
Oh, yeah, I didn't.
Yeah, so
I could have, but I did not.
I see.
But it's, All right. No, I know where it is. You're just wondering what the error is on the top quark mass. This guy, it's a couple GeV. Right, it's very small. Oh, plus minus, yeah, you're right.
Yeah.
It's 2 or something. Yeah, I'll put it in.
Okay.
Yeah, thanks.
Hi. I had a quick question about this plot you showed when you have an extra Higgs.
Uh-huh.
And then the Higgs productions.
Yeah.
Interference.
Yeah.
And yeah, okay, the peak and dip in this.
Yeah.
I understand. And so on the y-axis, this was normalized to the standard model, right?
Yep.
I don't understand why it asymptotes to the standard model value. I mean, what happens to this diagram where you exchange the heavy Higgs?
Oh, but it goes like 1 over mh squared. So it gets, the contribution away from the resonance of the heavier guy gets smaller and smaller.
Okay, but
Right.
the masses are not so.
They're not so big.
I mean,
Right.
So it's not so big with respect to the standard model Higgs. This is why I didn't.
Well, if you look, say, like at the blue, it's 300. So by the time you get out to 400, it's almost all asymptoted away. Yeah.
Okay.
It goes quickly.
Okay.
Yeah.
I guess I would have to compute it.
Yeah.
Okay, thanks.
I like those bump dips. There's an infinite number of papers on these interference terms. Yeah.
Okay.
Yeah.
Thanks.
Yeah.
I actually have a question related to this plot.
Oh, yeah?
So
Good, I like
why
this
is
plot.
the first peak so strong at 300 GeV? Because it seems to be, it's a log-log scale, so it's like the first peak is very strong. So I'm assuming
So
that
we're closer to the standard model Higgs.